Good afternoon, everyone. So, what we have seen in the last lecture, we have seen orthogonal transformation, right? And we have seen a property that the product of two orthogonal transformation is again a orthogonal transformation. Okay. Next, we want to prove that if you have finite rotations are not commutative, right? First one, we have found that suppose instead of going for this one, if we see in general, suppose I have any matrix, say A, okay, and suppose I have some another matrix, say B is equals to, and if I want to find out the product of these two matrices, that is A into B, whether it will be equals to B into A. Yes, can anyone answer whether it is equal to or not equal to B? Whether it will satisfy commutative property matrices?
No, ma'am.
No. So here also we have to prove the same thing that finite rotations are not commutative. Right? In the last lecture we have seen that the product of orthogonal transformation is again an orthogonal transformation. Now we have to see that finite rotations of a rigid body are not commutative. Of a rigid body are not commutative. Yes, let us assume that we have some matrix, say A1 and A2. So we can write so matrix A1 and A2 are not commutative. Okay. Now let us go for the next point, that is how to find out the inverse of a matrix. Okay. Now can anyone tell me how to find out the inverse of a matrix? How you found the inverse of a matrix up to now?
Minors adjoint काढून मॅम.
Hmm. After finding adjoint,
1 upon determinant.
Determinant A into adjoint
yes,
of
1
H.
upon determinant of A into. Okay. Now we have to find out the inverse of a matrix in this case. What we have seen in the last lecture, yes, anyone remember orthogonal transformation? How we have found the orthogonal transformation? Yes, we have found the transformation from x to x dash, then transformation from x dash to x double dash. Right? Anyone remember this one? We have written in the form of x dash is equals to x double dash, we have written in the form of x dash. And whatever this term we have, it is nothing but the matrix. Okay, the A mat. This is what B, and then we have found the product of two orthogonal transformation, which the transformation matrix we have found it is nothing but C. Okay. So here now we have to find out how to find out the inverse of a matrix. Okay. First we have found the transformation from x to x dash. Now in the reverse way we have to find out the transformation from x dash to x. Okay. First we will write down the transformation from x to x dash. Yes. What will be the transformation equation for transformation from x to x dash?
X dash k is equals to summation j over 1 to 3 bkj xj.
Okay. Now we have to write down the transformation from x dash to x, because now we have to find out the inverse of this transformation. That we can write it as xi is equals to summation over j aij dash xj dash, which means that this is a transformation from x dash to x. Okay, initially we have written the equation in terms of x dash is equal to. Okay, so now we have written the transformation from x dash to x. This is what a transformation from x to x dash. Okay, now we have to write down this whatever the term we have aij dash. This is nothing but your matrix A. Okay, this matrix A is a transformation matrix from x dash to x, this aij dash. Now we have to write down what is a transformation from x to x dash. It can be written as, now instead of using the I and j, the I parameter we have used already, I will write in terms of xk dash is equals to summation over I aki xi. Okay, this is say equation 1 and say this is equation 2. We have written the two transformation from x dash to x and transformation from x to x dash. Okay. Now we have to put whatever the equation we have obtained here, this xk dash, we have to put in our equation 1. Okay, in this way we can find out what will be the inverse. Xi is equals to summation over j aij dash xk j dash. Xk dash is equal to summation over I aki as it is. Now simply we have to write down what, instead of xi we have to write down this equation 1. That is aij dash xt. Now what will be the value of this term that we have seen in the last lecture? How to run this summation? Yes, can anyone tell me how to run this summation? And what is the value of this whole bracket?
Cij.
How it is Cij? See here, in this lecture we have studied what is a
The
transformation
matrix
from x to x dash. And next we have written the transformation from x dash to x. But in the last lecture we have written the transformation from x to x dash, next the transformation from x dash to x double dash. At that time we have a matrix A for x to x dash, and x dash to x double dash we have another matrix B. So for that case, we have written the matrix C, which is a product of A and B. But in this case, we have written the transformation from x to x dash, then x dash to x. Okay. Now, if I run the summation, what should I get after running this summation? Do you remember delta jk I have written somewhere in the
Yes,
last
ma'am.
lecture? Okay. If I run this summation, I have shown you also how the matrix is obtained. When I equal to j, it will be 1. Otherwise, it is equal to 0. A2 to A11. This is also 0 and the last term is 1. दाखवला होता ना हे लास्ट लेक्चर मध्ये.
Yes, ma'am.
Yes, ma'am.
Okay, after what you have to do for this term, you have to keep j equal to 1 and then run the summation over I. And then you will get somewhere these two are equal. If these two are equal, if I is equal to j, then you are getting 1. Otherwise, it is 0. Okay. Now, what we get, I can write this as summation over I aki aij dash, it is equal to 1, otherwise it is equal to 0. 1, then j equals to k, otherwise if j is not equal to k, then it is 0. Okay, so this I can write it as delta jk. So what we are getting here, this is what a transformation from x to x dash, and here we are getting these term as 1 or 0. So we will get the matrix of this type, 1 0 0 0 1 0 0 0 1, right? So what we can say about a into a dash, that means here we have written the combination of these two. Now we have combined the equation 1 and 2, but we have written xk dash and value of xi, that is our equation 1 we have used in our equation 2 here. So we have written the value of xi. So after this we have found that a into a dash, it is equals to 1 or 0, which we can write it as this matrix whatever we have obtained, 1 0 0 0 1 0 0 0 1. How we have obtained this matrix? Okay, first we have seen the transformation from x dash to x, which is written as xi is equal to summation over j aij dash xj. So what is a? A is aij dash, that is a matrix of a transformation from x dash to x. Next we have written the transformation from x to x dash, and this aki is nothing but a matrix A, a transformation from x to x dash. Okay, and this is what aki, right? This is matrix A, and this is what a matrix A dash, correct? So if it is A and A dash, we are getting resultant as either 1 or 0. 1 when j equals to k, otherwise it is 0. So this aki aij dash, I can write it as A into A dash. This is what a matrix we are getting, 1 0 0 0 1 0 0 0 1, which is nothing but 3 cross 3 identity matrix, and hence we get it as A into A dash is equal to identity matrix. Okay. Any doubt up to this?
No, ma'am.
So, what we can write after this step, I can write this A inverse is nothing but A dash. What is this A dash? A inverse is nothing but your A dash we have obtained. If I am having A into A dash is equals to I, so we can write inverse of a matrix can be obtained like this as with the help of this equation, A into A dash is equals to I, and hence we can say A inverse is equals to A dash. Okay. Now in the next part we have to prove this A dash is nothing but your transpose of a matrix, that is A2. How to find out the transpose of a matrix?
Interchanging rows and
By
columns.
converting row into column.
Okay. So in the next step, what we will do, whatever we have proved this step, into A dash is equals to, we have proved identity, so we have written A inverse is equals to A dash. In the next step, we will prove this A dash is nothing but your transpose of a matrix. Okay. So consider the orthogonal transformation from x to x dash, which is written as x to x dash. We can write it as xi dash is equals to summation over j aij xj. And what is A? A is a matrix which is be the matrix of transformation from x to x dash. Okay, which satisfy the orthogonality condition. What is the orthogonality condition? Summation over I aij aik it is equal to delta jk. What do you mean by delta jk? It is equal to 1 then j is equals to k. When j is not equal to k, it is 0. Now let us write down another transformation, that is a transformation from x dash to x. In that we will get a matrix A dash which is aij dash. Okay, just now we have proved A into A dash is equals to identity matrix. Okay, now we have the condition. What is the conditions? Summation aki aij dash, that is orthogonality condition, is equals to delta kg, which is equal to 1 or 0. Now we have to consider the double summation. Why? Because in this part we are going to prove this A dash is nothing but our A transpose. Just now we have proved A into A dash is equals to identity, that means A inverse is A dash. Okay, now let us consider the double summation. Summation AKL, both K and I, standing for 1, 2 and 3. AKL, AKI, AIJ, dash. Now what we will do for this one, first we will run the summation over I, then we will run the summation over k. I will write here sum, we will run the summation over I first and then we will run the summation over k. And in the next step we will do vice versa, that is first we will run the summation over k and then summation over I. Let me write down here. Summation over k, akl, this summation over I. First I will run the summation over I. AKI, AIJ dash. Okay, what is the value of this term we have written? This is equal to delta jk, AKI, AIJ dash. Okay, this as it is summation over k, akl. Again, if I run the summation over k, what will happen? If I run the summation over k, somewhere k will be equal to L. So what will happen for this term? It will be A L L. This will be delta L J. After running the summation over k, somewhere k will be equal to j, and this will be delta jj, and here we have delta jl. So what will be delta jj? It is equal to 1, because we say that if k is equals to j, then it is equal to 1. So we get here the term as ajl. Let me name it as say equation 1. Okay. First we have written here, we have to run this summation. For running this summation, first we have run the summation over I, then we have to run the summation over k. After doing these steps, we are getting the equation as AJL. Okay, we are getting the term as AJL. Now let us do the reverse procedure. For that, let me keep summation over I outside. We will run the summation over k. That is summation over k, akl, aki, this aij dash outside, because we are going to run the summation over k first. So what is the value of this term we have from our above equation? I have written here. This is a delta decay orthogonality condition. Okay, so I can write this as delta Li, the summation over I as it is, and ai j dash. After running the summation over I, this summation over I, that means this I will be equal to L. Somewhere the I will be equal to L. So we can have this is as delta LL, and this is A L J dash. What is the value of delta LL? It is equal to 1, and we get it is as A L J dash. This is equation 2. Right. So first we have got the summation after running the summation over I first, and then summation over k. And here we have run the summation over k first and then summation over I. So if we get these two equations, we can write this as aj l is equals to alj dash, which we can say what is this ajl, or if you are confusing with this L, we can write this equation as AJI is equals to AIJ dash. What is this AJI? It is nothing but A transpose, converting rows to column or column to rows. And this AIJ dash is nothing but A dash. And what is this A dash we have obtained here?
A inverse.
A dash we have obtained as A inverse. So from the last theorem we can write this A transpose is equal to A dash is equals to A inverse. So here we have proved this A dash is nothing but your A transpose. Hence we can write from last theorem A inverse is equals to A transpose. Okay, any doubt?
No,
No,
ma'am.
ma'am.
Now we'll see what is the determinant of this orthogonal matrix. Just now we have proved A inverse is nothing but A dash. This A dash is nothing but A transpose. Okay. So just we have written A into A dash is equal to I. We have proved just now. A into A dash is equals to I. What is this A dash? A dash is nothing but A inverse is equals to I. Identity matrix. Now if I take a determinant on both sides, what will happen? A inverse is equal to determinant of this identity matrix. What is this A inverse? This A inverse we have proved it is A transpose, which is equal to identity matrix. Now can you tell me what is a determinant of A transpose if you know the matrix A? Whether these two are same or different. Determinant of A
Same,
inverse
Same,
ma'am.
and
ma'am.
A transpose. Hmm. What is the value of these two? Determinant of A,
Same
determinant
येतात
of
मॅम
Same,
A.
ate,
दोघी.
ma'am.
Yes, both are same. So can I write this as determinant of A square is equal to identity. Determinant of identity matrix. On the next step, we can write it as determinant of A is equals to plus or minus 1, because we know that what is the determinant of identity matrix. If it is 1, and taking square root we can get determinant of A is either plus 1 or minus 1. So what is the determinant of orthogonal matrix? It is either 1 or minus 1. Okay. Now next we have to show that infinite rotations of a rigid body are not commutative. Infinitesimal rotations of a rigid body are commutative.